Yeah, Prahladh, you can start.
Good. Thanks. Okay. Yeah. Welcome everybody. So we will continue our discussion on the polynomial method. So recall from last time, we had proved this, the Schwarzschild lemma. We had basically shown that this was an extension of the basic maxim we had seen for polynomials, for univariate polynomials. For the univariate case, we have seen that if you're given me a degree D polynomial, a univariate degree D polynomial over a field, then it has at most D roots. We wanted to consider an extension of this to multivariate. You can't say it has at most D roots. A multivariate polynomial has have potentially infinitely many roots. It can be 0. But what we can do is to sort of look at this format. That is, let P be a polynomial of degree at most D. Similar to the univariate setting, it's a degree D polynomial where the degree is now the total degree of the polynomial. It's an M-variate polynomial. S is some grid. So S is some set of F, and you're looking at the polynomial, on this sort of, let me write this. You're looking at it in this sort of a grid. That took longer than I thought. So you're looking at this polynomial on this S to the M grid. That's the polynomial. So you're given the polynomial P on S to the M cross F, and you're told that P is not equal to 0. The claim is this polynomial can, the fraction of place where it can be 0, this is the 0 set. This can be very small. It is at most D over F, D over size of the grid. T over the length of the grid, not size of the grid is S to the power M, the length of the grid. So the probability that the polynomial is 0 is at most D over. Okay, this is the same statement which was true in the univariate setting, and we proved this by induction, with the base case being the univariate setting. Okay, the proof was very simple and all of this fine. Why is this a useful theorem? So what we will start off is, we will start off by looking at a couple of applications of, we'll see 2 applications of the polynomial identity lemma. This lemma has been discovered multiple times in the math and CS communities. It's more commonly been referred to as the Schwarzschild lemma. So what are the 2 you'll see. And 2 to bipartite matching. So let's go to the first one. So what's the problem here? The problem here is as follows. You're given matrices A, B, and C. And think of them as matrices coming from some finite field n cross n. They're all n by n matrices of finite field. And the goal is to check if C is in fact equal to the product of A, B. So that's what we want to check. We want to check C is equal to A, B. Of course, we know how to do matrix multiplication. You can do this. But notice that matrix multiplication, what's the complexity of matrix multiplication? What's an upper bound you can take? So let's assume you can add and multiply two field elements in constant time. Let's assume you can add and multiply two field elements in constant time. So if you have an n by n matrix, how much time will you require to compute? So let's ask this one. So that's the goal. So of course easy. So question is can do with me. So can do if you do matrix multiplication. Certainly, if you have the time to do matrix multiplication, you can multiply out the two matrices A and B and actually check AB equals C. So something you can do. I want to do something more efficiently than this. And why am I doing this? Let's look at the cost of matrix multiplication. So even before cost of matrix multiplication, let's ask a more basic question. If A is a f n cross n and B is a vector in f n cross 1, how much time does it take to compute? Time taken to compute AV. I want to compute this vector AV. How much time will it take you?
N square 9.
N square is an upper bound because each element AV is also a vector. Each vector is a dot product with a row of A and a column and this column vector V. That has n operations, n multiplications, and then n minus 1 additions. And you have to do n such operations. So certainly this can be done in order n square. Now, what about AB in Fn cross n? The same thing you can say, time to compute AB. This is repeatedly doing the same thing for you do V as just several columns. Each column of V as a V vector and doing the previous thing. So it's n times the previous thing. Certainly you can do it in order n cube time. You can do it in order n cube time. But a lot of work has been going on and trying to find out matrix multiplication to actually see if you can do this much more efficiently than n cube, because you're applying the same matrix A to this one. So therefore, it's not like AB for different ABs each time. Each time you're using the same matrix A. The matrix A, it's not just n computations of the previous step. If it's n computations of the previous step, if both A vector was changing and the V vector, A matrix was changing and the V vector were changing, then it actually n times the previous step. Here the V vectors are changing. The V's are the various columns of B. But A vector is the same vector as before. The A matrix is the same single matrix. So somehow can we amortize this cost and do it? There's been a lot of work and we don't know. So the matrix multiplication, the cost of matrix multiplication, it has to be at least omega n square because it has to output a matrix of size n square. So at least it has to take write down the n square elements. But we do not know what is the other end, how large is matrix multiplication. There will be, of course, n cube is this one. So there's been a lot of work starting from Strassen had an algorithm, this one, and the current best algorithm for this is n to the power and I believe it is 1 second. I don't recall the order of so the current best is n to the power 2.3728 something. This is due to Virginia Williams and Andrew Stockers. And let's in general call this n to the omega. A conjecture is that omega is 2. That is actually you can do matrix multiplication in n square time. That's a conjecture out floating around for a while. And it has been, the exponent has been steadily coming down and there's been active work on this one. What we now know, okay, fair enough. This is random, this is deterministic computation. But now I'm not actually asking you to compute matrix multiplication. I'm giving you C, the product, and I'm giving you AB and I'm asking you to check if AB equals C. can we do this faster? So it's not the same as actually asking you to compute AB. I just want to check if AB equals C. So question I'm asked, is checking easier than matrix multiplication? Is checking matrix multiplication is easier than matrix multiplication itself? And what we will show, surprisingly, is the following answer. We will actually give an n-square algorithm, a randomized n-square algorithm for checking. That is, if omega is greater than 2. If omega is less equal to 2, of course, it's not a more efficient algorithm. It's also an efficient, but you will see it's a much simpler algorithm. It's matrix multiplication is a much more complicated algorithm. We will see a much direct algorithm. And the algorithm is going to be the following. So what's the algorithm? I'm going to use randomness. So the input is A, B, and C. The algorithm, we will pick a random V, say from, if it's a finite field, I'll pick it from F to the N. If it's the rationals, I'll pick it from some S to the N. S will be some set of numbers. S will be some finite set. And then check if ABV equals CV. Now you'll say, how do I make this check? The way to make this check is not first compute the product AB and then V. The way we will do this is by doing it in the following fashion. We'll compute BV, then we'll compute ABV, and then we'll check C. That's going to be the algorithm. So notice it's the running time of this algorithm is 3 times order n square. Because you're computing CV, you're computing BV, then you're computing ABV. So you're never doing the matrix multiplication. You're only doing the first of the two operations, as a matrix vector computation. Now let us check the correctness of this algorithm. The correctness. So if AB equals C, then certainly the algorithm, you're going to check if this one and output yes, no accordingly. So this is the algorithm output. If AB equals C, of course, the algorithm outputs yes. There's no way the algorithm can output it. It's computing the same matrix on both sides. What if AB is not equal to C? That's one case. So in particular, if you look at this matrix D equals AB minus C, this matrix D is not the zero matrix. It's not the all zeros matrix. And what we are checking is if D is not equal to 0, what is the probability that when I pick a random V, DV is 0? This is exactly the question we are asking. This is the question we want to know. What's the probability that this happens? Of course, if D is 0, probability that DV is 0 is 0. Is 1. Now the question is, can this be 0? Now, if D is not 0, there is at least one row in D which is non-zero. All the rows can't be 0. So D looks like such a matrix. D is such a matrix. This is D1, D2, Dn. D not equal to 0 implies there exists an I such that di is not equal to 0. So probability that dv is equal to 0 is certainly less than or equal to the probability that the inner product between di and v is equal to 0. Because certainly at least this row and this thing should be this. It has an even smaller event than this. It's at least this guy. Now what is div? Div is just this. Well, what is this quantity? Just look at this. What is the probability of this? What is this? This is just summation dij vj. This is a univariate. This is a multivariate it's an n-variate polynomial of degree 1. And we are asking how frequently can this be 0? This is the Schwarzschild tells you it's at most 1 over size of S if V is being chosen randomly from S to the M. So so if you choose S to be a large enough, if the elements of this, whether you choose it, this works over every field. You choose S to be large enough, you just drive this probability. The probability that you will you pick a non-zero matrix and you multiply it with a random vector V. So the random vector is just by picking each element uniformly at random from some set S. The probability that this will become 0 is going to be 1 over size of S. So this is a super because you have to at least read the input. The input is n square long. You have to read the input. Okay. Any questions on this? Are people okay with this? It might seem like a cheat of an algorithm, but it is a remarkable improvement from n cube to or n power 2.376 to n square. And the power is you're basically throwing in randomness into it, and you're saying because you have to do only verifying matrix multiplication, not actually performing matrix multiplication, you can conceivably do better, and then you're throwing randomness over it, and it becomes far. You are actually able to do it in n square. By the way, this is called this is due to Freewald's, and this is called Freewald's algorithm. It might seem trivial, but this is important enough. There's a whole, I think, Wikipedia page devoted to this algorithm. Okay. Any questions on this? We will move to a more. It's a very important. It's a very clean algorithm, but it seems very simple. And you might not buy this as a buying part of power of the Schwarzschild lemma. The next application we'll see, it's actually going to be a stunning application. Is checking bipartite matching. So what's the problem here? So the input is you're given, let's call it a bipartite graph, a left, right, and a set of edges. So you're given this sort of a graph, left set of vertices, right set of vertices, and a bunch of edges. And let's assume mod L equals mod R is of size n. The left and right side are this one. What we want to ask the question is there perfect matching in G? The input is this graph G. So what's a perfect matching? I want a subset of the edges so that every vertex in the left side is mapped to every vertex in the right, and there should be 1, 1. It should be a bijection. a subset of vertices. Happens. Of course, you can check all this. There are Hall's theorem for way of checking this. Hall's theorem is one way of doing it. You can do all those checks, but I want a far more efficient. We can do this. There are algorithms to do this. Once again, I want to ask, does the power of randomness and combined with the polynomial identity lemma actually give you, can you do this more efficiently? Okay, is the question clear? Any question? And the algorithm is going to be completely bizarre. So what we'll do is we'll look at the sort of the bipartite adjacency matrix of this graph. What's the bipartite? I'm going to look at a n by n matrix. L is this side, R is this side, and Aij. What am I going to put in Aij? Aij, I'll put in one. This is the bipartite matrix. 1 if ij is an edge, and 0 otherwise. Let's put, this is the bipartite adjacency. So we can assume that the input has been presented to us this way. It's been given as this bipartite adjacency matrix. Okay. What we will do, so is the matrix clear to people? So this is, it's the rows are indexed by the left side, the columns are indexed by the right side, the right set of vertices, and you put, and it is a 0-1 matrix where 1 represents if the ith element from the left side adjacency matrix corresponding to a perfect matching will be a permutation matrix. It will be basically a 0-1 matrix, which is in which every column has exactly 1-1 and every row has exactly 1-1. That's when it's a perfect matching. Because everything in L should have a right thing. So all we are asking is there a permutation matrix sitting inside, supported in this bipartite adjacency matrix? That's the question we are asking. So now let's do something completely bizarre. I'm going to construct, so let's call this matrix A. I'm going to construct the matrix AX, and where X is coming, X is where X bar is XE, E belongs this. It's an E dimensional vector, size of E dimensional vector. These are a set of formal variables, xi1, xij's. And what am I going to do? This is exactly the same matrix as before, except that what I will put is ax of ij is going to be the variable xij if ij is an edge and it is 0 otherwise. It's exactly the same matrix as before, but we have replaced every one with a completely different variable. Every one we are putting a different variable out there. Is the matrix clear to you?
Not quite. Can you repeat?
So is the original bipartite adjacency matrix clear?
Yes.
So you take that bipartite adjacency matrix, it has a bunch of zeros and ones. Now every one, you replace it with a completely new variable. There are as many variables as the number of ones in this matrix. Okay. How many ones are there? The number of ones is exactly the number of edges. I'm just thinking of a new matrix of variables now. It's not a matrix of 0, 1. Is my voice not clear?
Yeah, it was breaking in between.
Yeah, there are some.
Yeah.
Problems. I think the internet is.
A lot of things are bad from my end today. Yeah, so do ask me questions. So
Also
it's the same matrix. You take the bipartite adjacency matrix. You take the bipartite adjacency matrix. It has zeros and ones. Replace the ones every one you replace it with a fresh variable. So for example, the one at the ijth, if at the ijth entry you had a 1, you replace it with a variable xij. This is a different variable from say I prime j prime. And the number of variables you have to put in is exactly the number of edges. Now, why am I doing this? This seems very bizarre. Now this is a matrix I'm going to look at. Let's look at determinant of A of X. What is the determinant of A of X? By definition, determinant is this object. We all know this. It's the, you go over all, you have seen the definition of determinant. You go over all permutations in Sn. It's the sign of Sn. Sign of, you go over all permutations sigma in Sn. Sign of this one, it's the product of Ax I comma sigma I. It's this object. Now let's look at what this object is. This is true for any matrix. This is how a determinant is defined. Now let's look at what happens to Ax for this particular matrix. I claim that this is exactly summation sigma in Sn. What will this be? This is exactly sine of sigma. Now sigma corresponds to a matching. Sigma corresponds to a matching. Now if that matching was not there, the edge of that matching was not there, the corresponding Axij is 0. There's one thing, so this term will drop out. This term will survive only if all the edges in the matching are actually there in the graph. Otherwise, this term will become 0. So for this, basically, this is going to go over all the matchings. It was then going to, it's going to be the indicator. It's going to be the indicator if sigma is present in E times pi xi sigma. Because if sigma is not present in E, there won't be a corresponding variable xij. If sigma is present in E, xi sigma I will actually, this is, you follow what I mean by sigma is in E. Sigma is this matching is in E. Okay. So what do we get out of this? Notice, and any two terms in this, two different matchings involve two different set of variables. They'll never cancel out each other. So the thing, what the main observation I want to say right now is determinant of Ax is a non-zero polynomial if and only if E has a bipartite matching, has a perfect bipartite matching. Are people with me so far? But now I know how to compute. Now how do I check? So now the algorithm is very simple. Just plug in random values for these xij's. Now compute the determinant. If the determinant is non-zero, that is a witness to you that. So what we will do is, this is the following algorithm. So let's pick. Let's say pick Bij at random from S, which is sitting in some field. We'll figure out how large a set he has to pick. So let S be a subset of F of size. Let's figure out what size to be later on. Compute A of B. A of B. If 0, output no matching, else output matching. That's the algorithm I'm going to give you. Now notice, if the graph did not have a matching, so now let's look at, this is a very simple algorithm. If you know how to compute determinant, it's super easy. So you just plug in these numbers, you compute the determinant. And determinant is something we know very efficiently to compute. Gaussian elimination gives you an n-cube algorithm to do it, but there is actually much more efficient algorithms to compute determinant. In fact, there's a very parallel algorithm also to compute determinant. Let's not forget, let's assume determinant is an easy algorithm. What does this algorithm say? So let's look at let's prove the correctness of this. So let's look at the case G does not have a matching. G does not have a matching, then certainly AX is identically equal to 0. As a polynomial, it's identically the 0 polynomial. Therefore, you will always output no matching. Algorithm always outputs no matching, because it will, no matter which B you pick up, it will always output, it will always be 0. Now let's look at the other case. G has a perfect matching. In this case, AX is not identically 0. What is the degree of AX?
N.
It is an n. It's a determinant. So if there's anything, it will be an n. So the degree is n. Therefore, what are we asking? We are picking a B at random from S to the size of E, and we are asking what is the probability that A of, sorry, this is what am I saying? It's not the degree of A of X, it's the degree of the determinant of A of X is n. The degree of the determinant of A of X. A of X is a matrix, it's a determinant of A of X. What's the probability that the determinant AB is 0? This is at most n by size of S by the Schwarzschild lemma. So you just choose yes to be, to pick these numbers from, say, a size of 100n. So just choose yes to be. So if you just choose this to be, say, 100n, you get that this case is 1 over 100. You choose it arbitrarily. So it gives you a randomized algorithm. It gives you a super efficient randomized algorithm to check if the graph is bipartite or not. The Schwarzschild lemma. So which is notice the algorithm. Otherwise, to do this algorithm is actually fairly tedious algorithm. You would have seen this in your, if you have done an algorithms course, this is one of the first algorithms. It's a non-trivial algorithm. But this is, you apply to polynomial identity lemma. It's a super clean, efficient algorithm. It of course comes at the cost of randomness. It's a randomized algorithm. So there's a probability of error. But this error you can drive it down to 0. It's an amazing algorithm to do this. So people with me? Any questions on the algorithm? Okay. Yeah. So Schwarzschild lemma or the polynomial identity lemma has tons of such applications. These are two cute applications. You can, there have been several theses. There's been actually a decade of, 2 decades of work in complexity, possibly just use the Schwarzschild lemma over and over again. It's just repeated applications. So in some sense, you can view the people might have heard of something called the PCP theorem. The PCP theorem applies the Schwarzschild lemma. There's something called the IP equals P space, which uses Schwarzschild lemma. You would have heard of the deterministic polynomial time algorithm for checking if a number is prime or not. Hidden inside it is the Schwarzschild lemma. All of these use the Schwarzschild lemma in various guises and forms. Okay. Questions? Any more questions? If not, we'll go on to the next topic, which is the combinatorial null still results. Okay. Combinatorial. So what is happening here? So let me first state the problem, and then we'll see some applications of it, see why it is useful, and then actually go into trying to prove the result. We'll do the other, not the sequence we followed for Schwarzschild. We proved it and then saw some applications. We'll do it the other way. So let say F be some field, and S1, S2, Sn are subsets of F, and let's say each Si is of size Ti plus 1. So I'm going to look at a grid we are going to look at this grid S1 cross S2 cross Sn. We are going to look at this sort of grid S1 cross. We are going to look at an n-variate polynomial S1. So and let F. So it's an n-dimensional grid. So let F be an n-variate polynomial with the following features. The total degree of F is D, which is actually T1 plus T2 plus Tn. That's the total degree, which is 1 less than the size of each element of the grid. And furthermore, let's assume the coefficient of x1 power t1, x2 power t2, xn power tn is non-zero in F. So F is some polynomial, and this particular, it's a non-zero polynomial. It's a formal polynomial when you, so I should have put capital X1, capital X2, capital X. The coefficient of this is non-zero. Then I want to say there exists an point A1, A2, An in the grid S1 cross S2 cross Sn such that F of A1, A2, An is not equal to 0. So once again, you have this n-dimensional grid. The grid, unlike in the Schwarzschild lemma, the grid lengths are not necessarily the same. They are of different lengths. T1, they are of length T1 plus 1, T2 plus 1, Tn plus 1. That's the grid lengths, the grid sides. And now I'm given a polynomial f whose total degree is the summation of ti's. And I furthermore tell you there is the coefficient of x1 power t1, x2 power t2 is non-zero. Now I want to claim if this were the case, this polynomial cannot vanish completely on the grid. There will be a place where it is non-zero. This theorem is not hard to prove at all. We will see the proof later. But what I want to say is it's a very simple theorem. I'll give you some cute applications of this and then we'll go on to the proof. So is the state, let's stare at the statement of the theorem. Are people okay with that? Let's first. So once again, you are given a grid, an n-dimensional grid, whose side lengths are t1 plus 1, t2 plus 1, tn plus 1. Then you are given a polynomial in n variables, whose total degree is this t1 plus t2 plus tn. So it is 1 less than the sum of the length, n less than the sum of the length of the grids. And furthermore, it's a non-zero polynomial, and it's not just non-zero. You know, a particular monomial in it has non-zero coefficient. Then I want to claim that this happens. Okay. Question. So let's actually see.
Just want to make sure I get this thing. Xi can be only from Si, right? That's what this means.
Which one?
A variable xi can take values from Si.
No, it's a formal variable. So it's a function is a formal function. So the xi can take only this. So, but I'm claiming there is a thing within the grid, a point within the grid in which it values is 0. The function could be, the polynomial could be defined possibly on the entire space,
Right.
not necessarily on the grid. So the polynomial is defined all over, you know, an f to the n, where f could be an infinite field, finite field, I don't care. But all I'm claiming is if you only care about the evaluation of the polynomial on this grid, and the grid has these dimensions, and there's a particular coefficient which is non-zero, then this polynomial cannot vanish fully on the grid. There will be so it's similar in spirit to the Schwarzschild in that sense. There is a point where it's non-zero. Schwarzschild is a more There's a quantitatively stronger statement actually. It says, what's the fraction of non-zero points? It puts a lower bound on that. It says 1 minus d over f are actually 1 minus d over s are non-zero. This is saying 1. So there is actually a souped up version of the Schwarz-Zippel lemma which actually implies this also, but we will keep them as two separate things. So let's see two applications first, and then go on to the proof of this statement. The first application will be actually an application from math. It's called the Cauchy-Davenport theorem. So the statement, before I say the statement, so let's work in some field. Let's work in FP, which is the prime field. P is prime. So P is a prime number. FP is this field. It is 0, 1, 2, 3, all 2, 3, all the way up to P minus 1. So this is the field. It's a finite field. And let A and B, two sets. By the way, it's important. This is a finite field and it's a prime field. The statement is going to be false if it's not a finite field, and you'll see shortly why that is false. That A, B be two subsets of FP. Any two arbitrary subsets of FP. And I'm going to define this class A plus B. The set A plus B. What is it? It is just all possible combinations. It's A plus B such that A is in A, B is in B. Take two elements, and one element from A, one element from B, add it, and the set of all such guys is called A plus B. The A plus B is this new set. This one. What I want to ask is, how large can A plus B be? If I give you A and B, how large? The question which we want to ask, Cauchy-Davenport question is, how large can A plus B be? What do you think it can? So I want to make it as small as possible. I want to make it as small. What's the best setting of things to keep it as small as possible?
I mean, mod A plus mod B.
Huh?
I mean, no, you want to ask. This was a guess.
Mod A plus mod B a guess. So I'm going to say, actually, I want to say,
mod A, mod B. Maybe.
Oh, mod A, mod B. No, I want to say it can be much, much larger than that. So one example is the setting is, if A, so think of so it's a prime field, think of P as a large number. So A, I'll put things like 0, 1, 2, 3 up to some A, say. And B, I will put 0, 1, 2, 3 up to B. So what will be A plus B? Let's assume A and B are much, much smaller than the primes. Therefore, if you add anything, there's no overlap. This is certainly 0, 1, 2, 3 all the way up to A plus B. That's all you can get. You can't get anything more than it. Let's assume A plus B is less than P. Therefore, there's no overlap happening. How large is this compared to A and B?
As in comparison, I mean, this has A plus B plus 1 elements, and those have.
So notice in this particular setting, A plus B is of size mod A plus mod B minus 1. And I claim that this give me any A and B. By the way, this is not, these are two numbers. I could have given any two. I could have given one AP of length A, another AP of length B, which have the same common difference, and you add them, you'll get the same thing. This is what will happen. So when you take A is an arithmetic progression, B is an arithmetic progression, and both the arithmetic progression have the same difference, then A plus B will just be also an arithmetic progression which will have exactly A plus B minus 1 elements. So you know that it will be this large. My question is, this is the best you can do. That is, anything else, sorry, this is the worst you can do. Anything else, this is the one in which there are most overlaps. In any other possibility of A plus B, then thing will actually grow very, very large. And that's the Cauchy-Davenport theorem. So the theorem due to Cauchy-Davenport is the following. So P prime AB subset of FP, then size of A plus B is greater than or equal to, I want to say, A plus size of B minus 1. It's almost true, except that if this number goes larger than P, certainly A plus B can't be more than the number of this one. So it's going to be the minimum of this and B. So that's the Cauchy-Davenport theorem. Is the statement clear? So the example I gave is that I want to say, you give me any other A and B, it actually will grow much, much larger. Is the statement of the theorem clear? Okay, so let's look at a proof. It's going to be a very Cauchy-Davenport. This was not the proof they gave, but it's going to be a very simple application of the combinatorial Null-Lanzar's theorem. So, by the way, it's important it's a prime field, because if it's not a prime field, suppose it was not a prime field, but a sort of, if it was a field, if it was another finite field, it was a field, it's a prime power field. Every prime power field has a subfield sitting inside it. So if A and B were the subfield, A plus B was not going to grow at all. If A was a subfield, B was a subfield, A plus B will be the same subfield. There won't be any growth. The A plus B will be the size of A. It won't grow as A plus B minus 1. Here I'm saying it becomes at least like twice of the size minus 1 or some such thing I'm saying. If A were a subfield, B were a subfield, A plus B will remain in the subfield. It never goes beyond the subfield. That's why it's important it was a prime field. If it's a non-prime field, this is not true. And we'll see that in the proof. There'll be a place in the proof where we actually use that P is prime. Okay. It's important that P is prime. The statement is false for non-prime fields. So now I'm going to split it into two cases. If mod A plus mod B is greater than P, in which case the minimum is actually P. In this case, I'm going to say, in this case, I'm going to say that A plus B is actually, in fact, will not be hard to see. Let's look at this. In this case, what do we want to show? In this case, I want to show actually A plus B is the entire set of this one. And that's not hard to see for any x in FP. Look at the set A and look at the set x minus B. X minus B is exactly x minus B as you range B over B. These two elements, so A and x minus B, size of A plus size of x minus B is greater than P. Therefore, they have to have an element in common. And if that element in common will mean that if you choose that A and that B, x is equal to A plus B. So I want to claim every x can be written as some A plus B in this set. Hence, that implies that A intersection x minus b is not empty. That is, there exists an a in a and a b in b such that a plus b equals x. And this is true for every x, hence mod a plus b is equal to fp, and we are done in this setting. Okay, so we'll work with the case in which mod a plus mod b is less than or equal to p. So a plus b minus 1 is less than p minus 1. Okay, so for contradiction, let us assume, let's assume mod a plus mod b is less than or equal to p minus 2. Sorry, oh, that's not what I mean. What I mean is the following. What I mean is mod a plus mod b is less than or equal to mod a plus mod b minus 2, smaller than this, which is a number smaller than p minus 2. Just for contradiction, let's assume this. So let C be any subset of superset of a plus b such that mod C is equal to p minus 2. So if C is not already, if a plus b is not already of p minus 2 size, just add more elements to make it p. And do I want to do this? Sorry, I don't want to do this. I want to do so that this is equal, this is exactly equal to a plus b minus 2. I add more elements so that I get a plus b minus 2 elements. If it is less than or equal to it, it could be much smaller, but I'll just add more elements so that it adds to this. Now let's look at this polynomial. Let's look at the polynomial fxy. I'm going to define it as product C in C of x plus y minus c. Is the polynomial clear? It's a bivariate polynomial defined on this set. So let's ask several questions. What is, so firstly, what is, let's ask, what's the degree of f?
Size of C.
Size of C. Let's look at the coefficient of x power a minus 1 and y power b minus 1. What's the coefficient of this?
One.
Is it 1? I don't want to say it is 1 because you have to pick x. So you have to pick x. You have x plus y power c. If it was x power c, if it was x power c, it is 1.
Yeah, okay.
So in every term you have out of the c terms, you have a minus 1 terms, you have to pick x. B, the remaining guys you have to pick this one. So this is exactly equal to size of c times size of a minus 1. C choose a minus. These are the number of guys you pick. This is exactly, this is a plus b minus 2. Choose a minus 1. Now this is not equal to 0 in FP. As a binomial coefficient, notice this is an integer, but we are working in the prime field. So this could become 0 if this number was divisible by p. But this is not equal to 0 since mod a plus mod b minus 2 is less than p. So if you write this as the binomial coefficient, this number will never have multiples of p sitting inside it. Therefore, this will be a non. So this coefficient is non-zero. Therefore, if you look at, and now let's look at f on the grid mod a, mod b, mod a cross, sorry, on the let's look at f on this grid. F1 A cross B. Now the combinatorial Null applies. Therefore, there is a point in A cross B because I have the degree of F is C. There is the coefficient is non-zero. Therefore, there is a point in the grid such that there exists A in A, B in B, such that FAB is not equal to 0. But this violates the thing because I'm saying that C contains all possible sums. If it had contained all possible sums, FAB had to be 0 for every point on the grid. This contradicts that A plus B is contained in C. And hence mod A plus mod B is at least mod A plus mod B minus 1. So I don't know the original proof of Kosher and Davenport, the Kosher-Davenport theorem, but this is the proof via combinatorial null subsets. Okay. Any questions on the proof? Okay. We'll go to the next application, one more application of combinatorial. So let's look at the statement. It's a nice statement. It says that if you give me two sets, the sum of the two sets will only, if you're working in a prime field, it's only going to keep increasing, and it will increase at least additively. Yeah, of course, if there were subfields, this might not happen because you might not increase in size at all. A plus B will be the same subfield. But it says once you remove any possibility of subfields, this is just going to increase by this one, and arithmetic progressions are the only exception. They are the tight example of this, by how much you can increase. Okay. So the next application, the application 2 is covering the Boolean hypercube. With hyperplanes. So this is a sort of a puzzle sort of a question. So I'm looking at the Boolean hypercube, which is 0, 1 to the n. It is these 2 power n points, and think of them sitting in R to the n. So it's these 2 power n points and this one. What I want to now do is I want to pick up, and what's a hyperplane? A hyperplane is basically something of the form summation ai xi minus plus b equals 0. That's a hyperplane. Now I want to pick up hyperplanes such that I cover all the points in the Boolean hypercube. I want to pick as few hyperplanes as possible such that the question is how many hyperplanes are needed to cover B. So let's call each such hyperplane H. That is, what is the minimum M such that there exists H1, H2, Hm hyperplanes. So that for all x in 0, 1 to the n, there exists a I such that Hi of x is 0. Every Boolean point is in some hyperplane or the other. Now, this question is actually a trivial question. The answer is 2. I can choose the hyperplane x1 equals 0, x1 equals 1. That's going to cover the whole thing. So to make the puzzle interesting, I want to cover all points but the origin. The hyperplanes should not cover the origin. So the question is not, so this makes it not interesting. So what we will do is, we will take the same question. To cover t minus the origin. That is, what's the minimum? This one for all x minus the origin, and there does not exist an I such that hi of 0 is 0. So the Boolean, the all zeros point is not covered. Okay. So that's the alternate. So this is question 2, and that was question 1. And here I want to say there are multiples. Here, one answer for it is I could choose x1 equals 1, x2 equals 1, xn equals 1. These are n hyperplanes. They together cover, because every non-zero point at least has one coordinate to be 1 and is covered by the corresponding hyperplane. This is one setting. Another setting is summation xi equals 1, summation xi equals 2, and so on up to summation xi equals n. These are also n hyperplanes. They also cover this one. Notice, but both of them have n hyperplanes. The question is, can you do it with fewer this ones? And what we'll see is actually you cannot. If you drop off this one, you need n hyperplanes. And surprisingly, n is necessary. And we will prove this using combinatorial steps. So that's the statement I want to make. Okay. The proof is via combinatorial. So suppose h1, h2, hm cover b minus the origin and don't cover the origin for some m which is strictly less than n. Okay. Now let's build up. I'm going to build a polynomial f x1 xn in the following way. So we can, so without loss of generality, in particular, each of the HIs do not include pass through the origin. Therefore, they have to have a constant term. They can't be this one. Because by scaling, we can assume that the constant term is 1. So we can, without loss of generality, we can assume that each HI of x bar looks like 1 minus some linear function in x. I'm just going to scale it so that that constant term is 1. So now I'm going to write I'm going to define this object. What happened? This guy, I'm going to define it to be pi into 1 minus Li of x, I going from 1 to m, minus 1 minus xi, let's call it j going from 1 to n. I'm going to define this n-variate polynomial. Okay. Once again, now let's look at what is degree of f. What's the degree of this polynomial? So the degree over here is at most m. The degree over here is n. And m is less than n. Therefore, the the degree n term here cannot be cancelled by this guy. The largest degree here is strictly smaller than this. Therefore, the degree of f is in fact exactly equal to n, the largest degree guy. And further, we know that the coefficient of x1, x2, xn, this is exactly equal to -1 per n, which is not 0. Now let's look at the grid. Now let's look at f on 0, 1 cross n. So this is the grid I'm talking about, 0, 1 cross 0, 1. So notice in the combinatorial Null-Ansatz, Ti was 1 now, because the coefficient of each xi is this one. Sorry, let's go back to the combinatorial Null-Ansatz. What's the statement of combinatorial Null-Ansatz? So each Ti is 1, and the grid is of each dimension is 1 larger. Therefore, I'm taking grid of size 0, 1. That's all I'm choosing. So let's go back to this. So the combinatorial Null-Ansatz will tell you there exists an A1 to AN in 0, 1, n such that f of A1 to AN is not equal to 0. But I claim this can't be true, because for all A in the origin minus not the origin, this is 0 as well as this is 0. Because if something is not the origin, it's covered one of the lines, and it's also not this one, so both of them are 0. But if it is the origin, this is going to be 1, this is going to be 1, it's still 0. So for all points in the origin, the HIs are a cover, HIs cover, and hence f of A is, HIs cover A, f of A is 0. For A being equal to 0 to the n, you can actually compute it explicitly. This is just 1 minus 1, which is 0. So on the whole grid, it is 0, but you have count this one. Therefore, our assumption that m is less than n is false. Hence, m greater than or equal. Okay. Questions on this? So the combinatorial Null-Ansatz has had, it's a statement due to, I should have mentioned whom it is due to. It is due to Noga alone. It's a very simple, it's due to Noga alone. It's a very simple fact, but it has it's not a profound theorem of its own, but it has stunning applications across. There is various theorems like the Kosher-Davenport theorem. These are all deep theorems in math, have been proved using just this very simple application. Very simple.
Prahladh, can you go to the last line again? Oh.
Of which one?
The final theorem you proved, right?
Yes.
The contradiction we found.
Yeah.
I see. So here, did we need combinatorial Null-Ansatz, or would Schwarz-Zippel also give this to us?
No. Schwarz-Zippel would not have given to you. Schwarz-Zippel, the degree is n. So it will give you n by, its degree by s. So the s is of size a, 2 here.
Oh, I see.
So this is a place where actually you need the combinatorial Null-Ansatz. There is a spruced up version of Schwarz-Zippel which subsumes the combinatorial Null-Ansatz. That would have sufficed for it. There's a spruced up version of Schwarz-Zippel which involves the individual degrees also. That would have implied this, but that's just a bigger version of both the CN and Schwarz-Zippel together. But for this, the way I stated Schwarz-Zippel, that's not strong enough to prove this. We needed, because the length of the grid is very small. It's only 2. It's only 2 over here. And Schwarz-Zippel, the numerator will be the degree, which is n. N by 2 is a useless number if you're talking at probability.
Yeah.
Okay. So clear? Okay, so let's go to the proof of the combinatorial. So the proof of the combinatorial lemma. It can be proved directly in one shot, but I don't want to prove it in one shot. I'm going to break it up into parts and prove it. To tell you why the name combinatorial Null-Ansatz comes about. Null-Ansatz is a deep theorem in mathematics. Why does it call combinatorial Null-Ansatz? So let's go into. I will take possibly 5 minutes longer or so, 5 or possibly more, but I'll finish this proof. Proof of combinatorial. That's what we'll do now. So even before, so you might have heard something called Hilbert's Null-Ansatz. That's where the word comes. Let's actually spend a little time on what that is. So this name, what is Hilbert's Null-Ansatz? Hilbert's Null-Ansatz is a deep theorem from algebra. It says take F to be any field that is algebraically closed. What do I mean by algebraically closed? That is, if you take any polynomial in this field, it has a root. For example, the rationals are not algebraically closed because x squared plus 1 does not have a, you have to go, the complexes are algebraically closed. Finite fields are not algebraically closed because you can always come up with a polynomial which doesn't have any roots, but there's an algebraic closure for every finite field, which is, every field has an algebraic closure. These algebraic closures will be infinite. This one. So let's work with this. Yeah. For instance, for this purpose of this thing, just think of F to be the complexes. It's algebraically closed. Any polynomial in the complexes, any univariate polynomial in the complexes does have a root. And let G1, G2, Gm be n polynomials over n variables. So these are m univariate polynomials. Do I want them to be univariate? No. They're m. So m n variate polynomials. And you also have another polynomial f, which is in. Suppose I give you these m n-variate polynomials and a special f, such that for all points in the field, for all vectors, for all a in this one, if G1a equals G2a equals GMA equals 0, if you take any combined 0 of all the m polynomials, that also happens to be a 0 for the function f. Suppose you had this property, that is, on the vanishing set of G1 to Gm, f also vanishes. Then I want to say f has to be, so of course, if f can be written as a combination of the Gi's, this is true. The Hilbert's Null-Ansatz says this is the only way it can happen. What Hilbert's Null-Ansatz says is, then there exist polynomials h1, h2, hm in x to the n such that f is summation gi hm. By the way, this is false the way I have stated it. There exist polynomials and an integer k. K is a positive integer, so that f to the power k looks like this, not f. F need not look like this. F to the power k looks like this. And there's a reason why f to the power k happens. Is that you won't be able to show f is the sum of the gi's. You'll be able to show that there's some power of f. But for zeroness, this is sufficient. Notice it. For zeroness, this is sufficient. This is Hilbert's Null-Ansatz. It's a very deep theorem in mathematics. It's the basis for a lot of things. Hilbert proved this for us. What we will show is there are special cases for which this theorem is actually trivial to prove. And combinatorial Null-Ansatz is a consequence of that. So it steals the name Null-Ansatz. This one, Null-Ansatz, is a very deep theorem. It requires a lot of It's a deep theorem. It requires a lot of maths to prove it. The combinatorial instance search will actually prove it in 5 minutes right now. We're going to prove a version of it in 5 minutes, but it's similar in spirit. The statement is similar in spirit to Hilbert's null search. That's why it's called the null search. Is the statement of Hilbert's null search clear? So if F also vanishes from the combined vanishing set of the G's, then F has to be, a power of F has to be some polynomial combination of the G's. That's what Hilbert's null says. This is true only in algebraically closed fields. It's not true otherwise. In non-algebraically closed fields, this need not be true. Okay. So the CN, the proof is simpler. Firstly, M is equal to N, and each GI of X was actually of the form pi of Xi minus S in Si. So suppose each GI was just this univariate polynomial. GI could be an n-variate polynomial, but suppose I force each GI to be just this univariate polynomial, which is just the polynomial which checks if the ith variable comes along this grid along the ith quadrant. So GI is just that polynomial. G1 is checking whether the first variable is along the first is a member of S1. G2 is checking if the second variable is a member of S2, and so on. So each of the GI. In this special setting, I want to say actually, see, M is equal to N, and then I want to say if you have the case if F satisfies. So let's write this theorem. Then the proof of Hilbert's null search is simpler. And this is a theorem which we first prove now. I'll state that. And here I don't need algebraically closed or any such thing. So let F be any field. Let F be any field. S1, S2, Sn are subsets of F. GIs are the GI of Xi is the polynomial defined as above. It's defined as Xi minus S in Si. And I'm just stating it in a weird fashion. I'm stating that for all A in F to the N, if GI of G1 of A equals G2 of A equals Gn of A equals 0. What does this say? This just says A is a point in the grid. That's all. This is just a fancy way of stating. Suppose we had that. This implies that F of A is 0. This is just a very fancy stating that F is 0 on the grid. It's just but I'm writing like this because it now looks like the hypothesis is similar to the hypothesis of the Hilbert's null search. Then I want to say so G and F is some polynomial in of x1 to xn of degree d. Then there exists h1, h2, hn in F such that two things are true. Such that one, F is summation gi hi, and two, for all I, the degree of hi is less than or equal to d minus size of Si. So in this case, no f power k or anything is needed. F is actually equal to summation gi hi, and each h is of degree at most d minus Si. Notice that this is sort of G is itself the degree of G was the degree of Si. So this is d minus Si. So together it is of degree d. So is this theorem okay? This is sort of what I will call the easy null-Stillen routes. And we'll prove this in 2 minutes. But I want to state that if this is true, what the statement of combinatorial Null-Ansatz is true. So let's call this the easy Null-Ansatz. The statement clear again. In the special case when m equals n and g's are these polynomials, it says that if a function is 0 on the grid, the only way it can be a 0 on the grid, if I give you a degree d polynomial which is 0 on the grid, it must be a linear combination of these polynomials gi, and linear in the sense it's not multiple by scalars, multiple by polynomials. Gi times hi. Hi's are not scalars, hi's are polynomials. Let's just, before we prove this, let's see a quick proof of the combinatorial Null-Ansatz from the easy Null-Ansatz. So we are given an f. We are told that the degree of f is d, which is t1 plus t2 plus tn. Let's recall. And we are told that the coefficient of x1 power t1, xn power tn is not equal to 0. And we are given si, so that size of si is ti plus 1. We want to say that f is non-zero on the grid. There's a point on the grid, it's non-zero. So let's assume for contradiction that f is 0 on the grid. Assume for contradiction that f, when restricted to the grid, is 0. Now the easy Null-Ansatz will say, the easy Null-Ansatz implies that f is equal to summation gi hi. What is this? This is summation hi into product of xi minus s in s. And easy Null-Ansatz implies this, and the degree of hi is less than or equal to t minus size of si. So in our case, this is exactly, yes. This is exactly summation. And let's look back to this. What's the sum? This one, this is summation ti minus, summation tj, j going from 1 to n, minus ti plus 1. That's the degree of h. So f is written of this. Now let's look at, what do we know? We know the coefficient of x1 to the power t1, xn to the power tn is non-zero in f. This is what we have been told. Let's look at, it has a non-zero coefficient this side. Let's look at this side. What can it be non-zero coefficient? So this is the largest degree. This is the largest degree in this. And we know that to get the largest degree, you have to pull out the largest degree term from here and the largest degree term from here. There's no other, if you don't pull it out, the degrees are smaller because of this condition. You have to pull out the largest degree from gi and the largest degree from hi in order to get such a term. But what is, if you pull out the largest degree from gi, what is the largest degree from gi? What's its power? Gi is the recall.
Size of si.
It's the size of si. It's ti plus 1. So it's xi to the power ti plus 1. So if you pick up the largest guy from here, it's going to have xi power ti plus 1. Therefore, certainly it cannot generate this guy in xi term. So none of the terms in the summation can ever generate this guy. Therefore, the coefficient of this guy on the right-hand side is 0. There is no term on the right-hand side that can generate it. But the left-hand side, you're saying the coefficient of non-zero. This is a contradiction. So the easy Nullstellan search immediately tells you that such a thing cannot happen. And the reason is because we assumed f was non-zero everywhere. So f has to be non-zero. This is a contradiction. In f is not equal to 0. However, coefficient of x1 power t1, xn power tn is 0 in summation gi hm. That's a contradiction. Hence, there exists a in S1 cross Sn such that f of a is not equal to 0. That's the end of this proof. Okay. I will take a little more time. Finish the proof of the easy Nullstellan search and then wind up. People with me so far? Any questions? This one. The proof of combinatorial Nullstellan search is simpler than what I have done. I made it a big fuss talking about easy Nullstellan search. That was all just to tell you why the name Nullstellan search comes. Otherwise, it seems, why would you use this name Nullstellan search? Because it's a modification of, it seems like you can write it in a way which looks like Hilbert's Nullstellan search. It's actually a much easier theorem to prove. Now what we'll show is the proof of what I now want to do is proof of the easy Nullstellan search. Okay. And this is going to come from two nice observations. The first observation which I want to say, which will actually form the basis, this observation, I'll call it an observation now, but it's going to be the basis for everything I'm going to do in the next lecture. Is going to be the two facts. So let us look at, so we are working with the grid again. This was the first observation, S1 cross S2 cross Sn. So I'm going to define, and once again we are given each SI, should I make it of size Ti plus 1, let's call it this, Ti plus 1. This is the set of all functions on the grid. Let's look at this space. This is a vector space because I can take two such functions, add them pointwise, I'll get another function. I can multiply it by a vector space. It's the first one. So let's call this F1, and F1 is an F vector space. In fact, of dimension what? Of dimension, what will be the dimension of this? It's just a table. What is a F? Each element of F is just a table of values. It's the dimension of this is just S1 cross S2 cross Sn. This is just the dimension of this vector space is this. So it's just a list of all functions of this type. For every under the grid, you give this. Okay. Now I'm going to look at, so this is F1. Now I'm going to look at F2. What is F2? F2 is the set of all polynomials F belongs to Fx1 to xn, such that the degree in the ith variable of F is at most, what do I want it to be? It at most Ti, that is equal to size of Si minus 1. So it's not, I'm not controlling the total degree, I'm controlling the individual degree. Notice this is also a vector space. I take two such polynomials, I add them up, it will still remain such a polynomial. I multiply it by an element of the field, it will still remain. So F2 is also an F vector space. And what of what will be its dimension? Its dimension is basically the number of possible monomials, because once you have the monomials, all you determines is which coefficient you're going to put before the monomial. And how many monomials exist in this? What's a monomial of this form? It's x1 power a1, x2 power a2, xn power an, where the ai's, each ai is less than or equal to ti, this one. So each ai gets ti plus 1 choices, because it can take 0. So notice that this is exactly of dimension. It will be of dimension t1 plus 1 cross t2 plus 1 cross tn plus 1, which is exactly the same dimension as what we had said before. What I want to say is these two are actually the same object. They are now two vector spaces. They have the same dimension. What I want to say is, of course, I can't say they're the same object. One is functions, one is polynomials. What we'll show is we'll show a bijection between them. And once you show so in fact, now you only need to show, what we'll show is we'll show a mapping. We'll show that any function this way, once we show any function from F1 can be written as a polynomial, then it will show a bijection, because now that will show surjectivity. That will show it will show surjectivity. Once you have surjectivity, you have the whole. Okay.
Prahladh, maybe I'm saying something plainly wrong, but it isn't. So these are polynomials, but I mean they are functions.
They are also functions. So all I want to say is when you view these polynomials as functions, you get these functions above.
Yeah. So isn't both of these are vector spaces? Isn't F2 a subspace of F1?
Which is a subspace? Huh?
I mean,
F1. You're asking is F2 a subspace of F1?
Yeah.
For that, you need one fact. You need to show that two distinct polynomials don't map to the same function. They could be as polynomials, two distinct polynomials, but they could become the same function. Basically, you could have a polynomial p in F2 and a polynomial q in F2, which goes and maps to the same function. Then it's not a subset.
Right. No,
Which is basically stating, is there why does this come? Is there a non-zero polynomial in F2 that maps to the zero function on F, which is exactly the question we asked for. Is there a function on the grid which, when you view it as a polynomial, is non-zero? And in some sense, this is what the combinatorial Null is all about. Is there a function which has this feature in which all of this is being I want to say this, so as two polynomials can vanish on a set. But I want to say that these polynomials, this set of polynomials do not vanish. If it's a non-zero polynomial, it does not vanish on this grid. That's basically the point. Once you say that F2 will be a subset of F1 that way, and because the dimensions match, F2 has to be equal to F. Okay. Now, why this one? So how should we prove this? How should we prove this? So let's for this class just assume that this happens. That these two are the same set of classes. I'm already overshot a lot of this one. I want to say there's a bijection. That is F1 and F2 are, that is F1 is isomorphic to F2, which is the same thing as saying if you give me a non-zero polynomial, from F2, when you view it as a function, it is a non-zero function. So there's a bijection between them. That is, two different polynomials cannot get mapped to the same function, which is the same as stating that a non-zero polynomial cannot get mapped to the zero function over there. Let's defer this proof to the next time. But given this simple fact, this is a very simple fact, this is a very simple observation. Let's finish off the proof of the easy null sums. Okay, so the easy Null inserts. So I'm given f. F is some polynomial of degree d, and I've told that f on the grid is 0. And the GIs are polynomials defined this way. GI of xi is product of xi minus s, s and s. We're going to do a very simple thing. So f of x1 to xn. Think of this just as a polynomial in x1 now. And let's just do division by x1. So I can write this as g1 of x1 into some h of h1 of x plus some remainder polynomial. I've just divided this one and said that the degree of R1 with respect to x1 is strictly less than t1 plus 1. G1 had degree t1 plus 1. Therefore, when I do this division, just taking a large polynomial, dividing it by let's view it as a univariate polynomial. Think of the other variables are all as constants. Just dividing by g1 of x1, the remainder polynomial will have degree certainly smaller than the degree of the polynomial I'm dividing it by. Just let's do this step again. So g1 x1, h1 x1. Notice that h1 has the property that I want. h1 will have a degree d minus s1. One. Right? Now do the same thing for this one. So it's g2x2 h2x plus some r2. Now I'm viewing r in this one. I brought the degree down. Now you'll have the degree. R will have the property that the degree in x1 of r, that the x1's degree is not going to shoot up by that. That is going to be less than t1 plus 1. And furthermore, the degree in x2 will also be less than t2 plus 1 for this process. Further dropped it. So you keep on doing it this way, you'll get it to be summation gixi, hix plus rn x1, x2, xn. You get this. But with the caveat, so the GI with that the degree in xi of ri is 0. Is not 0, is less than ti plus 1. But what do we know? We know that f is 0 on the grid. F is 0 on the grid. This is 0 on the grid. Therefore, R also has to be 0 on the grid. Because this point is 0 on the grid completely. F is 0. All I want to say is F restricted to S1 cross Sn is 0. And GI is 0 on the grid on this thing. That implies that Rn, so this is Rn, sorry. So Rn on the grid has to be 0. Now I go to the fact that Rn is a function. As a function, it maps to 0. Therefore, Rn as a polynomial has to be identically the 0 polynomial. This is where I'm using f1 and f2 or this one. Therefore, Rn as a function, Rn of S1 cross S2. So Rn as a function is 0, and but Rn is an element of f2 because its degrees are all less than this. That implies that Rn has to be the identically 0 polynomial. It cannot be anything. Hence, f is equal to summation g of h. So that's the understood. So the easy inference is an easy thing. You just divided one after one by g1, g2, gn. You got the remainder polynomial. The remainder polynomial had low degrees in all, individual degree in all of them. And you knew it vanished identically on the grid. Therefore, I claim it has to vanish. It has to be the 0 polynomial. It cannot be any other polynomial. That's all. already spent past time. Let's stop this. I'll quickly recall this at the beginning of next lecture and prove this F1 is isomorphic to F2. Okay, let's stop with this. Sorry for overshooting time. I think let's stop. Yeah. Any questions? I'll post this. You ask me not on this. Ask me on Academy if you have any questions. Okay then.